Okay, so we are going to be doing a chi-square goodness of fit test. We're going to start with our data, and let's say that we have different colors of M&Ms. And so the different M&M colors we've got are blue, green, yellow, orange, red, and brown. Now, if we actually had M&Ms and we were to count up the different colors, so these would be called our observed counts. And so here's some numbers from old data I have. Let's say we have 53 blue, 28 green, 35 yellow, 50 orange, 11 red, and 13 brown, for a total of 190 M&Ms. Okay, now M&Ms has on their website, you can go on and they actually have a distribution for what percentage of M&Ms are each color. So here is M&M's claim that 23% are blue, 15% are green, 15% yellow, 23 orange, 12% red, and 12% brown. So using this, what we want to do is we want to compare M&M's distribution to what we got. We want to see, is their claim the same? So I'm going to create a new column, and we're going to call this is called the expected count. Expected counts. Now, everything that you do with chi-square is all about counts. And so we've got percentages, and if we have 190 M&Ms and we would expect 23% of them to be blue, well then in order to get the expected count, what you would do is take 0.23 times 190. If we expect 15% to be green, we're going to take 0.15 times 190. So I'm taking each of these percents and multiplying it by 190. Okay, and you don't have to write this. You do have to show this expected column, but I want you to see for your notes where this is coming from, because if anything gets messed up, it's usually right here. And so when I take these, I'm going to get the expected counts and multiply them. So this will be 43.7, 28.5, 28.5, 43.7, 22.8, and 22.8. for a total of 190. Now, some chi-square distributions that you do, they might have a where everything's equally distributed. So let's say that M&M's claims that their distribution is equally distributed. Well, then you would have 6 colors, so you would take 1/6 of 190, 1/6 of 190. So it just kind of depends. So in your homework, if you're doing a problem where you might have an equally likely distribution, you could just take your total and divide it equally by 6, and that would give you the expected counts. So now, this column, expected counts, what I'm gonna do is compare these, and if you'll notice, like 13 is, 11 is it's like almost double what we had is what they claim, and the 28 is pretty darn close for the green. So some of these are close and some of these are off. Well, we don't want to just look at the difference of these, because we have better methods, more advanced methods that will help us to really see, does the claim fit our sample? And so we're going to create this new column. And this new column is going to be calculated by taking the observed minus expected squared divided by expected. So we find the differences, then we square them to magnify the differences, and then we kind of bring them all down to the same level by dividing by the expected counts. So I'm going to have my calculator do this for me, as you will too. So we're going to go and we're going to enter our data into L1 and L2. Okay, so I'll just start this over with you guys. So 53, 28, 35, 50, 11, and 13. So that's the observed counts. The expected counts, 43.7, that's going into L2. 28.5, 28.5, 43.7, 22.8, 22.8. Okay, now L3 is going to calculate this new column, observed minus expected squared divided by expected. So I'm going to open parenthesis, make sure you are highlighting L3, and we're going to take observed, which is L1, minus expected L2, close parenthesis, square that, and then divide by the expected, which is L2. Okay, so you should have that on your calculator so you can see that. Press enter, and we're going to copy these into this row right here. 0.0087, 1.4825, 0.90824, 6.107, and 4.2123. Your expected these, and what this does is you guys are actually starting to calculate the chi-square value. So the chi-square is when you sum all of these values. We actually call this portion right here, these are all the chi-square components. And so if we want to see which one is contributing most to the difference, you'll notice which numbers are the highest. So look at the red. See how that's 6.107? Look at the greens, which was very close, the 28, and the expected counts were 28. Notice how that's really close to 0, because if you took 28 minus 28 squared divided by 28, you're going to get 0. So the ones that are showing the biggest difference are the red and the brown. And so those are contributing most to the chi-square statistic. The chi-square statistic comes from adding all of these up. So let me show you how to do that in your calculator. So go to the home screen, and we're going to go to second list. Arrow yourself over to math, and we are summing L3. And we're at 14.69. Or 698, whatever you want. And so that is the chi-square value. So now let me show you how we're gonna, I'll show you at the end how this is gonna work with finding our p-value. Okay, so first of all, if you're doing a chi-square goodness of fit test, you better make sure that I'm seeing a column of expected counts, I'm seeing a column of observed minus expected squared over expected, and I'm seeing the chi-square, all that added. So these definitely have to be here. These will be graded. So again, we're doing a significance test, and so we need our HO and our HA. So the null hypothesis is M&M's claim of distribution of colors is true. The alternative is that M&M's claim of the distribution of colors is not true. Okay, you can even say, like the distribution of colors fits what the claim is, goodness of fit. So the assumption is, well, why would we think that it's not true? So you always assume that, yeah, that it fits, the distribution fits, or it is true. So HO and HA. And again, we have to have our conditions. So we're going to write conditions for a chi-square goodness of fit test with, and we do have degrees of freedom, and it's categories -1. So the categories that we have are up here. Will you shut the door? Thank you. 1, 2, 3, 4, 5, 6. So we have 6 categories -1. So that's 5 degrees of freedom. So it's actually not the sample size. It's categories -1. And so 5 degrees of freedom. So number 1, you've probably guessed it already. Is it a simple random sample from the population of M&Ms? And in this case, I'm going to assume this to be true. Okay, number 2, we are sampling without replacement. So is the population of M&Ms greater than 10 times n, where n is still your sample size? So we have 190. 900. So there are more than 1,900 M&Ms in this world. These come together to make sure that we have independent M&Ms. And as I always tell you, it's that third condition that's going to be where you have to stop and think. And on a chi-square distribution, we want all expected counts to be greater than 5. And if that's true, a chi-square distribution is okay to use. So notice the therefore there, all expected counts. So I have to go back up to the expected counts column and notice every single one of these is greater than 5. You do have to be careful. If it's not greater than 5, what we could do is we could combine categories to try to make sure that they do get. So like for instance, I could say I'm going to put the red and brown together, which will make a larger number, and you get your expected count to be greater. So if it doesn't happen, that's usually what they would do. So all expected counts greater than 5. So now we're going to draw our chi-square distribution, which you guys have not seen before, but is going to look like this. A skewed to the right distribution. Chi-square. And if you look at here's your grape sheet. That's the chi-square distribution. Critical values. It's always skewed to the right, and it's because it's calculated by squaring values, so everything's going to be greater than 0. And chi-square is going to go on the curve. You're always shading to the right. So our chi-square was 14.698. You still do have to show a formula. So the formula for chi-square is at the bottom of page 5, where we've been using all year. Right there at the bottom it sneaks in. Chi-square test statistic. Observed minus expected squared over expected, the summation. So you'll just have to show me a couple. So you're going to write the formula. Observed minus expected squared over expected. And you can abbreviate that like that. I'm fine with that. And then just show me a couple substitutions. So we would take, for instance, the blue M&Ms. We would do observed 53 minus 43.7, square that, divide by the expected 43.7. Add that to, and then maybe show me the last one. So I'll do the browns, which are 13 observed minus 22.8 squared divided by 22.8. And that is equal to the 14.698. So show me the formula, show me a couple substitutions, and then show me your chi-square value. Now, in your calculator, once you have the chi-square value, we need to get the p-value. Okay, so where do you go? Under the distribution menu, you will see a chi-square. CDF is what you want to choose. So second distribution, chi-square CDF. Now what chi-square CDF is going to accept is you're going to plug in the chi-squared value, which is 14.698, comma, really large number, 999, comma, degrees of freedom. So our degrees of freedom were categories minus 1, so that was 5. Okay, and that's going to spit out a p-value for you, 0.0117. Okay, and I'm going to finish this up. So since the p-value is less than alpha equals 0.05, we will reject HO. Okay. There is sufficient evidence to conclude M&M's claim for color distribution is not true. Okay, we gathered enough evidence to say the alternative, that it is not true. So that's the test. That's everything run through. Some of you with newer calculators, the older calculators won't have this, but I'm just going to show you. So some of you actually have in the test menu, you can go down, you'll see a chi-square test, and it's chi-square goodness of fit, GOF test. Press enter. Some of you don't have this. It's kind of annoying, but L1 is your observed, expected is L2, degrees of freedom is 5. If you hit calculate, it'll actually do everything for you. So the rest of us will have to just go through, so there's your p-value. The rest of us are going to have to go through and do chi-square CDF, chi-square value, comma 999, comma degrees of freedom. Okay, that's how the rest of us. Now, just so you know, also with the chi-square test, these are the components. So if you arrow to the right, that's the chi-square component, observed minus expected squared. So these numbers, when I arrow to the right, are actually these numbers right here. There's the 0.0087. The 1.4825, 0.90, so you can see that. And that is a chi-square goodness of fit test. So how well does your claim fit your sample, or something old fit something new? And so the assumption is always that they are the same, they do fit each other, and the alternative is that they're not. Okay, so hopefully that works. Have a good day, guys.